Theodore Deden here, author of Business Python. I'm going to answer the question today, what is the difference between integers and floating point numbers? Now, there's an easy answer and there's a little bit more involved answer. First, the easy answer. An integer is anything that doesn't have a decimal place. 5 is an integer, 0 is an integer, negative 100 is an integer. You can have integers as big as you want. I can type in a whole bunch of numbers. That right there, what I'm typing in, is an integer. And Python has no trouble, at least in the newer versions of it, has no trouble taking care of that integer, looking at that, and I can say that, and I can subtract 1, I can do operations on it, I can also add, I can do whatever, and it will take it and it will process it accordingly. Now, a floating point number, in contrast, is anything with a decimal place. So if I take that same thing and I put a decimal place at the end, all of a sudden that's a floating point number. And you notice that it's showing me the floating point number now in scientific notation, 8.7236, etc., times 10 to the 63rd power. Fantastic. Now we have a nice representation of floating point number. We can also input floating point numbers in scientific notation, times 10 to the whatever 123rd power. That's fine. It'll take it just like that. Or we can take one and we can do something like that. And it's happy to take that number and represent it here. Now we can do operations just like we can. We can mix operations between floating points and integers to an extent. You do have to watch out a little bit for the automatic typecasting that does take place when you do that. But that's the easy answer to the question. The easy answer is that the integers are whole numbers like that. They can be positive or negative. The floating point numbers are ones with a decimal place. They can also be positive or negative. Now, what's the little bit more involved answer? What this all is suggesting, what this is getting at, is the fact that deep down in the belly of the computer, these types of numbers are dealt with in completely different ways. Now, as you know, computers have to deal with all data as ultimately as ones and zeros. One at the fundamental level generally being a high voltage, 0 being a low voltage. That's true, I think, for all modern computers. In the past, it wasn't always the case. Sometimes it was positive voltage, negative voltage. Sometimes the lower voltage was actually the 1 and the higher voltage was the 0. That was historical. But in modern computers, high voltage 1, low voltage 0. It doesn't actually make any difference because we are conceptually at a much higher level than that. We can think of them as simply as ones and zeros. Point is that the computer is dealing with these things as simply voltage levels, ones and zeros. If you want your computer to understand a little bit more about what your data is, you want it to be able to process it. Let's say you tell your computer you want to add two numbers together. That computer needs to know at the basic level how to do that. And you're going to add a number that is an integer in a bit of a different way than you're going to add a number that is a floating point number. Why? Because they are ultimately represented at the base level of the operating system, actually even below the operating system at the hardware level, they're represented in different ways. What ways are they represented? So there are standards that are in place for doing this. And if you open up a web browser and go to Wikipedia, you can see, for example, that integers use what's called 2's complement encoding. Now, this is in order to allow for the integers to be signed. So that you can have both positive and negative integers. Maybe before we even get there, let's take a look, let's remind ourselves just a little bit about how numbers kind of work. So I'll do this. Let me open up an Excel, just a blank Excel, and let me take a look here. So we have a number like 1,234. We're used to dealing with numbers like this. This is in base 10. What does this really mean? Well, we've got the thousands digit here, we've got the hundreds digit, we've got the tens digit, and we've got the ones digit. What this is really saying is we're going to take this and multiply by 10 to the, let's go ahead and do the caret notation, 10 to the 0 power, right? And this is multiplied by 10 to the first power, and this is multiplied by 10 to the second power, and this is multiplied by 10 to the third power. At its base, if we take 1 times 10 to the third plus 2 times 10 squared plus 3 times 10 to the first power plus 4 times 10 to the 0, which is 1, of course. Let me just make that a little bit more explicit here, write it in a little bit more familiar terms. And just so you can see it, let's zoom in a little bit more. So if you think about what we're doing here, this is how we represent in decimal how we represent our numbers. That's what they mean. Now, in binary, it's much the same way, except that instead of going all the way to 9 and then rolling over from 9 to 0 again, then adding that next place when you have to add the next one. And instead of having a base 10 here, we have a base 2. So we go to 1, and then immediately we roll over to the next place. And this is perhaps a little bit clearer if we look at something in binary. Let's take, for example, a binary 3. Now, binary 3 is going to be 0, 1, 1. Okay? Now, let's just make sure we can actually see that. Or let's even do it this way, 0, 0, 1, 1, just so that we can be a little bit more consistent with how that looks. Now that 0, 0, 1, 1, we're going to have, again, we're going to have a 2 to the third power. We're going to have a 2 squared place. We're going to have a 2 to the first, and then we're going to have a 2 to the 0. What is 2 to the 0? 2 to the 0 is still 1. 2 to the first is 2. 2 squared is 4. And 2 cubed is 8, right? Now, that 3 is represented 0, 0, 1, 1. Why? Because when we take 0, 0, 1, 1, when we take 1 times 1 plus 2 times 1, we get our 3, right? That's how that's working in binary. Now we're talking about unsigned binary. We can't here, we don't have any way of imputing a sign to this. This starts at 0. If it's 0, 0, 0, 0, it's going to be 0. 0, 0, 0, 1 is going to be 1. 0, 0, 1, 0 is going to be 2, etc. Now, how then do we do signed binary, signed integers? How do we represent signed integers? This uses a little mathematical trick, and what it does, we're used to seeing integers that when you're counting up, they're all preceded by zeros, and then you have basically the ones that are in there are representing sort of that offset from 0 in a positive direction. With signed integers, in contrast, specifically 2's complement, we start out with 1s, and the zeros are going to help represent how far away you are from 0 in a negative direction. Okay, now this is not really that intuitive to begin with, but we can look at a few examples. And now I'm going to go back to that Wikipedia page in 2's complement so you can kind of see. We looked at 3 before, that's 0, 1, 1. 0 is, of course, 0, 0, 0. And you don't have a negative 0. No, that's important to note. Now, there are other forms of binary representation of signed integers that do actually have a negative 0. It doesn't really make any sense to have a different representation for negative 0, but some of them do. 2's complement, however, does not. 2's complement, if you have 1, 1, 1, in contrast, that becomes negative 1. Negative 2 is 1, 1, 0. And if you needed to extend that backward, just like if you needed to extend this 3 backwards, you would put a whole bunch of leading zeros. If you need to extend a negative number backwards, you would have a whole bunch of leading 1s in that whole thing. This works out really, really in a very, very cool way, because what happens is if you need to add two numbers together, you can add them in exactly the same way that you would add two unsigned integers. So by using 2's complement notation, the exact same logic can be used in your computer at the hardware level to add the two integers together, whether they're signed or unsigned. And your computer needs to know if they're integers or not, but at the base level, it doesn't need to know that that they're signed or unsigned. So that's a really cool feature of two's complement, and that's how they're represented there. There's much more to learn about that, and it's really cool to learn. But for business purposes, you don't actually have to know that. I think that's we've already covered quite enough detail that you can understand what it's doing at the base level. Now, let's go back now to look at the floating point. How are floating point numbers represented? If you recall in our little example here that we can put in a very large floating point number here, 10 to the 63rd power or so, or 10 to the 123rd power, whatever it is, and this scales quite nicely. You can have very large and also very small. Remember, you can also have times 10 to the negative 20th power, negative 30th power. Let's say, for example, if you're looking at the size of viruses or individual molecules and things like that, and you're representing that as a scientist. Um, Hopefully, you wouldn't have those really small numbers in bank accounts and things like that. Probably the hundredths place is good enough for that. If you're counting the pennies, you're doing just fine. Be that as it may, the question is how then do you represent those floating point numbers in your computer system? And that is done typically by the IEEE standard. It's IEEE, I always forget the exact number, 754. That defines one of the main standards that are used also in Python for a uh, for a floating point number. Now, here, if you scroll down here, here's the Wikipedia page, you can see now that you have three components to that. It's no longer straightforward when you're looking at, for example, here we have a 4-byte word, 32 bytes, or sorry, a 4-byte word, 32 bits, right? You can have the same thing in an integer, and you don't have any division. It's not like you're slicing it up. But in the case of floating point, you do slice it up. You have this fraction part with the 23 bits here. You have an exponent part with the 8 bits, and then you have an explicit sign bit. And what that allows you to do is at the hardware level, now you can design specific hardware for all of the operations that you would have to do for multiplying, dividing, etc. with two floating point numbers. But importantly, the arithmetic that you perform at the computer base level on numbers that are represented like this in floating point is going to be different than on integer numbers. So the computer does have to be able to differentiate and know, hey, I'm representing a floating point number or I'm representing an integer, and that's important. In Python, it does come up in multiple times. One place it comes up, for example, is if you have a list and you have, let's define it as A, B, C, etc. Right? And then you want to use the index operator. Let's see, I'm going to take the second element, which is index 1, because remember, it's all 0 indexed, right? So the second element, my list 1, that is B. Now, what I can do is I can make the index that I take the result of an operation. I can make it the result, for example, of 1, or I can make it 0 plus 1, for example. And that expression is evaluated. 0 is an integer, 1 is an integer. When we add those together, we get an integer result, and that integer result is 1, so we get the exact same result. Now we have to be careful, because if we were to then add 0 plus 1.0, now we're mixing. Now we have, in fact, let's 0.0 plus 1.0. We don't even have to mix. We have two floating point numbers. This is completely unambiguous. Now we have a result of when we add two floating point numbers together, the result is going to be another floating point number, except that the index operator doesn't take floating point numbers. It takes integers, which means that when I hit enter right now, we're going to get an error. And here we go. There's the type error. Hey, a list index that you use with the index operator, it has to be an integer. It cannot be a float. It cannot be a floating point number. So how do we deal with this? Well, one way we can deal with this is we can typecast this, and we can say, okay, I want to convert that to an integer before running that. Now, there are a lot of automatic typecasts that happen in Python. So for example, if we take 1.0 and then we add a 3 to it. Now we're adding a floating point to an integer, and what we get is a floating point result. So we have an automatic typecasting in the background. That 3 integer was originally represented in 2's complement when it's read in by the Python interpreter, but then it gets converted to the IEEE floating point standard in order to perform that addition. And once that addition is performed, then of course the result is logically going to also be a floating point number that it gives in response. So you have to watch out for those types. That's what the difference is between the two. I believe I've answered the question by now. And if there are more questions to follow up on that, please feel free to leave them in the comments section and check out my other videos answering the other questions relating to business Python. Thank you very much.